Welcome to Brain Vision.
Hi everyone, so what we have is nitrogen gas flowing through a long constant diameter adiabatic pipe. At the entrance of the pipe it's at 100 psia and the temperature is 120 degrees Fahrenheit. And at the exit of the pipe the pressure is dropped to 50 psi and the temperature is also dropped to 70 degrees Fahrenheit. And what we're asked to find is the velocity of nitrogen at the entrance and the velocity at the outlet. So what we're going to do first is just go ahead and state our assumptions. So we are going to assume that this is a steady state process and that nitrogen is an ideal gas. And we're also going to assume that potential energy changes are negligible and there's no work interactions and there's no go ahead and write the work, and that heat transfer is also negligible. So what we can do is first find our properties for our nitrogen at room temperature. So the one thing that we're going to write down is our CP value, which is equal to 0.248 BTU per pound mass Rankine. And since this is a steady state problem and we're only dealing with one inlet and exit, our m dot at the beginning is going to equal our m dot at the end. And we're going to use the pipe as our system. So when we do our energy balance, we have the rate of the energy coming in minus the rate of the energy leaving is equal to the total rate of change of the energy in the system. However, since we said that this is a steady state problem, this is going to be equal to 0. So therefore, our energy coming in rate is equal to the rate at which energy leaves the system. We're going to go ahead and break these terms down into their components. And what we have is enthalpy and motion. So what we're going to do is going to say that the energy coming in will be equal to m dot h1 plus v1 squared over 2, which is the kinetic energy. And that's going to equal the enthalpy that's leaving, so m dot h2 plus the kinetic energy of the fluid when it leaves. So as you can see, we have m dot on both sides, so we can go ahead and cross that out. And what we're left with is the enthalpy and kinetic energy terms. And what we can do is actually go ahead and isolate our velocity terms onto one side and isolate our enthalpy terms on the other side. So we'll see that we have v1 squared minus v2 squared all over 2 is equal to h2 minus h1. We can actually go ahead and break down h2 and h1 in terms of our CP and temperatures. So we can say that v1 squared minus v2 squared all over 2 is equal to, in fact, CP T2 minus T1. So we actually just went ahead and resolved the enthalpies into the terms or into the conditions that we know, and that's temperature. What we can also do now is combine the mass balance and the ideal gas equation. And what this gives us is that we can say we know that m dot 1 is equal to m dot 2. And this is equivalent to saying A1 V1 all over specific volume 1 is equal to A2 V2 all over specific volume 2. And recall that the ideal gas law is P specific volume equals RT. And we can rearrange this equation here and solve for V2, and that'll give us that V2 is equal to A1 over A2 specific volume 2 over specific volume 1 times volume 1, which is equal to just V2 over V1 because the areas are the same because we have a constant diameter pipe. And this in turn is equal to P1 T2 all over P2 T1 volume V, and that is equal to volume 2. So what we can do now is substitute in this expression for V2 into the energy balance equation. And what this gives us is V1 for velocity is equal to 2 CP T2 minus T1 all over 1 minus T2 over T1 P1 over P2 squared mean square root of that. And plugging in for all these values and all for these variables, we get an initial entry velocity of 515 feet per second. Now we can also solve for our exit velocity using the relation we solved for before. So V2 is equal to V1 times P1 T2 all over P2 T1, and this gives us a velocity of 941 feet per second. And these are our final answers.